Hello everyone. So today we'll be solving some question related to week 6 content of control engineering course, and that is related to frequency domain analysis of system. So we'll proceed with questions. We'll try to understand the concept that is taught in the lectures through these questions. Okay, so let us go through questions one by one. This is the first questions. First question. Let me see if the recording is working or not. Yeah. So it says that I think I have to open it again. Okay. So this is the first question. It says that if input to a system with transfer function GS, which is this, is RT. So this is GS, which is S plus 3, and there is this input RT given to this, which is 7 cos 3t minus 40 degree. So what would be the steady state response of this system? So suppose yt is the output. So what would be yt yss density, a steady state value. Now if you see, the input is a sinusoidal input. So it's cos omega t plus minus phi, something like that. So from frequency domain analysis, we know that whenever a signal, suppose A sine omega t is given to system, which is a linear LTI system, so that is represented by suppose GS, then output will be B sine omega t plus phi. So there will be change in magnitude and there will be a phase shift. So what would be the magnitude of output, or you can say amplitude of the output? This will be magnitude of G of j omega into A. And what would be the phase of output? Suppose this is y dash and this is x dash. Angle of y dash will be angle of the x dash plus angle of G of j omega. Okay, so one thing that we can do is that we'll just find the Laplace transform of this one, and since this is input to this system, so output Laplace transform will be ys equal to rs into gs, and then we'll take Laplace inverse Laplace transform, and we can find what is the response of this system gs corresponding to this excitation, but that will give you overall response, and we want what? Steady state response. So we can take a easy way, that is this one, and since we know this, so we'll try to apply this concept only. So what is the input frequency? This is omega equal to 3. radian per second. Okay. So we have to find yt. Okay, we have been given input and we'll try to find what is the angle of magnitude and angle of g of j omega. So we'll just write g of j omega. We have g of s, so we can replace this complex frequency with this imaginary frequency. So we'll have j omega by j omega plus 3. Okay, and omega is 3. So we'll have j3 by j3 plus 3. Now if you simplify this, just multiply with complex conjugate numerator and denominator, you will get 0.5 plus j 0.5. Now we can write this as in the phasor representation. The magnitude will be 1 by root 2 and phase angle would be 45 degree. Okay, so now we know this one and this one. What we have to do? We have to find the steady state response. So what would be this? Since out input is 7 cos 3t minus 40, output will be some b cos 3t minus 40 plus 5. So this phi is angle of g of j omega, and this p we can calculate. B will be, okay, this is a into g of j omega, where omega is 3. Sorry. So what would we get? This will be 7 into 1 by root 2, and so therefore this output, which is yt, or we can say yss, so yss will be 7 by root 2 cos 3t minus 40 degree plus 5. So what is the value of phi or angle of g of j omega? This is 45 degree. We'll just add 45 degree. Okay. So what do we get overall? 7 by root 2 cos 3t plus 5 degree. So this is the steady state response of this system Gs when it is excited by this signal RT. Okay. Now let us see. We have got this answer. Okay. So this is application of this concept of frequency domain analysis of system, that when a sinusoidal input is applied to a linear LTI system, the output is when a sinusoidal with same frequency, only magnitude and phase changes. Okay, so let us proceed to next question. What does it say? That the amplitude and phase shift of an irrational transfer function upon Gs. So this is the transfer function, and we have to find the amplitude and phase shift. Now, so what can we do? How will we find? So we'll just find g of j omega. This will be e to the power minus 4 j omega by j omega. Okay. So we have to find magnitude. So what will be a of omega? This will be mod of g of j omega. So we find e2 minus j4 omega by j omega. What is the magnitude of e to the power j theta? Magnitude will be 1. So this is 1 and denominator will be omega. So this is the amplitude. Let us find the phase shift due to this transfer function. So phase shift is angle contributed by numerator. So this will be minus 4 omega, or we can say angle contributed by e to the power minus j 4 omega minus angle contributed by this denominator. So what is the angle contributed by this? This would be minus 4 omega, and since this is an imaginary part, so this will just contribute pi by 2. So if you see here, earlier what we had seen, we had a frequency. At a given frequency we found this value of amplitude and a phase shift due to transfer function, and for a given frequency we get some value. Now here also for each frequency we will get some value of a omega, like amplitude and phase shift. So what can we see from here, that as omega is increasing, this amplitude is decreasing. What about phase shift? Phase shift, this is constant and this is increasing with omega. So phase shift maybe in negative, so that will increase, and at omega equal to 0, what is the amplitude? This will be kind of infinity, and this will give, what will be the phase shift? This will be minus 90 because this omega is 0, so minus pi by 2. So if we say that Nyquist plot, if we try to plot the polar plot of this one, so what we get? So polar plot will be some kind of this, that this will be infinity, and as the frequency increases at this omega equal to 0, this is corresponding to minus 90 degree, and as this is increasing, the magnitude is decreasing and phase shift is increasing. It is kind of this kind of polar plot would be there, something similar to this one, not exactly but something similar to this one. Okay, so we'll move to next question. It says that an underdamped second order system of form this omega n square, which is the standard form that we have seen, omega n square by s square plus 2 zeta omega n s plus omega n square. This is a second order system. This is an underdamped second order system. Okay, has peak response 2.5. So MR is 2.5. So we have to find what is the damping ratio. Now for this system, we know that we can find, like if we try to plot the frequency response of this system, of j omega, so it would be kind of this, we have gone through in lecture, and at the frequency when it has maximum amplitude, this is the resonance frequency and this is the peak response MR. Okay, so for this, how do we find this value of MR? So obviously this M of j omega attains its peak at this value, so we just find, like we just differentiate M of j omega by with respect to omega, and whatever the value of omega it gets, this will give omega r. Okay, So what is this m of j omega? So suppose that this is omega n square by minus omega square plus 2 zeta omega n j omega plus omega n square. Now we'll just have a variable which is omega by omega n. So m of ju will be 1 by 1 minus u whole square plus j 2 zeta u. Okay. Now whether we want to find omega, so we can find, if we find u, then we can find omega also just by multiplying with omega. So if we differentiate with respect to u and equate it to 0, what is the value of u that we'll get? This will be 1 minus 2 zeta square root over. So if this is substituted in this one, then we get the value of peak response. So that will be mr, which would be equal to 1 by 2 zeta root under 1 minus zeta square. Okay, so once you find u, so what would be the omega r? This will be omega n root under 1 minus 2 zeta square. So this one is omega n root under 1 minus 2 zeta square. So fine. This is how we have, like, you must have gone in the lectures. We gone through the lectures, which shows that the frequency response of this underdamped system. So how can you find the peak overshoot? Okay. So now we know what is the formula for this one, and it is known what is the value of mr. So we can find zeta from here. So what we have, 1 by 2 zeta root under 1 minus zeta square equal to 2.5. Now if we simplify this, what we get? Zeta square, we can say zeta 1 minus zeta square equal to 0.2. This would give zeta square 1 minus zeta square equal to 0.04. Now if we say zeta square equal to 2, okay, so we can then have this equation 0.4 equal to 0, and we'll solve this. So what is the value of t that we'll get? T will be 0.0417 and 0.9582. So this is the value of t. Because it's a quadratic equation, we get two values of t, and from there we can find zeta. So zeta is equal to 0.2043 and 0.978. Okay, so there are two values of zeta, and we have been asked to find the value of zeta. Now if you see this u, which is omega r, so omega r is equal to omega n root over 1 minus 2 zeta square. Now this resonant frequency, or we can say frequency, that would be a real number, obviously, and that would be, so for that this should be greater than 0. So that is 1 minus 2 zeta square should be greater than 0. This means what? 1 is greater than 2 zeta square. So zeta square is less than 1 by 2. This implies zeta is less than 1 by root 2. Now if zeta is greater than this value, then this will be a complex number. This is not the case because frequency will be real number. Okay, so what is the 1 by root 2 value? Let us see. So 1 by sqrt 2. This is 0.707. Okay, so we got two values of zeta. One is 0.204 and one is 0.978. So obviously this is, but if this is the case, then there is no peak overshoot. The response is kind of like this. Okay, so we'll have just this value of zeta. So this is the answer, 0.204. Okay, so I hope this is clear. This is related to frequency response of second order system, because in second order system we saw that there are various types of response. Like for step input, it can be critically damped, under damped, then we had over damped. So therefore we had this different kind of border plot also. Basically, more undamped it is, more the peak will be, like that. So with zeta decreasing to 0, peak will increase. Okay, so let us proceed to next question. Next question says that the open loop transfer function of a unity feedback system is given by this one. Okay, so this is Gs, which is As plus 1 by S square, and there is unity feedback, and this input plus minus, and this is the output. The value of A such that phase margin is 45 degree. Okay, so what can we do? So we have gone through this idea of phase margin, that suppose there is a system and this is a GH plane. We have some Nyquist plot which is like this. This is the unity circle which is passing through -1 J0 in GH plane. So this, the point at which it crosses, okay, let's say the frequency at which this unit circle crosses this Nyquist plot is this gain crossover frequency, and if this is the phase angle of GH, it is a phase shift due to GH. So if this phase shift of this angle, that is theta, suppose more phase shift of theta is given to this Nyquist plot, then this will pass through -1 J0. So in that case, the system proceeds to verge of instability, because as of now it is stable. It is not passing through this point, or it is not enclosing this point, based on number of open loop poles in right up plane, and based on Nyquist criteria, which is n equal to p minus z. So basically the number of zeros should be, because this explains the number of poles of closed loop system, so this should be 0. So based on number of poles in right half plane for open loop system, the encirclement should be same. Okay. So what we have, so this is the phase shift, or we can say the phase shift that will be provided, this will be the phase margin. Okay, this theta. So this theta will be pi plus angle of GH. Okay, now here it is unity feedback, so H is 1. So GH will be simply G, and if we find G of J omega, we have J A omega plus 1 by minus omega square. Okay, let us see how can we solve this one. So we have GS, which is AS plus 1 by S square. Right. So it is saying that what should be value of S, such that phase margin is 45 degree. So what is the angle of G of J omega? This will be tan inverse A omega, and due to numerator, since this is S square, so it will have 2 into pi by 2, and this is unity. So tan inverse A omega minus pi. Okay, so this is the angle of G of J omega. Now what is the phase margin? Phase margin is pi plus angle of G of J omega. So this is pi plus tan inverse A omega minus pi. This would give tan inverse A omega. What is the value of phase margin? Which is 45 degree. So this is equal to 45 degree. So what is A omega? A omega will be tan 45 degree, which is 1. So this means this omega, which is the gain crossover frequency, will be 1 by A. Okay, so we know this much. Now this is gain crossover frequency at this point, or at this frequency. What is the magnitude of G of J omega? Because this is crossing the unit circle, so the magnitude at this point for this Nyquist plot, this is sample Nyquist plot, but the Nyquist plots of this system, this will be 1. Okay, so let us see what is the magnitude of this one. This is A square omega square plus 1 root over by omega G CF square. So this omega G CF is equal to 1. Now if you solve this, you get omega GCF square equal to root 2. Okay, so from there you can get A equal to 1 by omega GCF, which is root under 1 by root 2. And what is the value that we get? 0.841 if we solve this one. Okay, so this is the value of A, for which the phase margin of this closed loop system is 45 degree. So we can cross check this one also. Let us see if we can validate this using MATLAB. So what we have to do, we have this system. We'll just see how the Nyquist plot of this one looks like, and from there we'll try to find out what is the phase margin of this one when A is equal to 0.841. Or one thing that also we can do, we can try to see what is the Bode plot of this one, and whether at the frequency, which is the gain crossover frequency, the phase angle or phase shift which is required to turn the system to verge of instability is 45 degree. So let us see that. So let us then a system. What is the open loop system? This is transfer function with numerator, which is 0.841 comma 1 have 1 s square plus 0s plus 0. So this is the system. Now what we have to do, we have to find the Bode plot of this system. So Bode. Okay. So this is the Bode plot for this open loop transfer function, and we have to find stability margins. Okay. So at this point, if you see this one, this is 0 dB line, means gain is equal to 1. So 20 log 1 is 0 dB, with log 1 is 0. So we have this point, and at this frequency, which is 1.16 radian per second, we have to find what is the phase shift or phase angle. So if we see phase margin, which is 45 degree, so this is 180 degree minus 180 degree, and this much angle you can say less in terms of value is for this system. So this is 45 degree phase margin. Okay. So the value that we have got for A, this is correct. Now we will proceed to next question. Again, it says that open loop transfer function with unity feedback system given by gs equal to k by s, s plus 2, s plus 10. Okay. The value of k such that closed loop system is stable with gain margin 6 dB. Fine. So what is the gain margin? It is 6 dB. If we think of this Nyquist plot for this one, okay, so how it can be? This would be something kind of this. Omega equal to 0. This will tend to, magnitude of this will tend to infinity, and as omega tends to, because we'll find this g of j omega, so this would be k by j omega plus 2 j omega plus 10. Okay. So as omega tends to 0, this tends to infinity, and as omega tends to infinity, this tends to 0 with angle contributed by this, and this is minus 180 270 approx. Okay, so we just have a mirror image of this one. This will go like this, it will be very omega, and it will be like this. Fine. So if you see, what is the number of poles in right half plane for this system? G. Number of pole is equal to 0. Fine. So what is the encirclement of system, like encirclement of minus 1 J0 plus J0 is required. So n should be equal to P minus Z, and it is said that the closed loop system is stable. So that means Z is equal to 0. So n should be equal to P. The number of encirclements should be equal to P, and P we know it is 0. So number of encirclements should be 0. So that means this point should be outside this region. So suppose this is somewhat like at this point minus 1 0. Okay, so it says that the gain margin of this one, when what is the value of k, such that gain margin of the system is 60. So gain margin is what, that it crosses, when it crosses minus 180 degree, what is the gain by which, if it is like what gain, what by what gain value of gain, this k, this, suppose this is gs, so by what value of gain k dash gs should be multiplied so that this Nyquist cross passes through minus 1 0. So again this is like driving the system towards instability or verge of instability. Okay, so at least we know that this Nyquist rod does not enclose this point. So now we have, what do we have? Know that this gain margin is 6 dB. So, and this plot is crossing this point of 6 dB at page crossover frequency. So at page crossover frequency, what is the angle of G of j omega? This is minus pi, or we can say minus 180 degree. Okay, so what is the angle of G of j omega? This will be contributed by this and this pole. So this will be minus 90 minus tan inverse omega PCF by 2 minus tan inverse omega PCF by 10 equal to minus 180 degree. Okay, so what we get from here, we just simplify this one. This is tan inverse. So this would give us tan inverse omega PCF by 2 will be tan inverse omega PCF by 10 equal to 90. So we know tan A plus tan inverse A, tan inverse B, summation will be tan inverse A plus B by 1 minus AB. This will be 90 degree. Okay, so once we solve this, what we get? Omega PCF by 2 into omega PCF by 10 is equal to 1, and this means omega PCF is equal to root under 20 radian per second. So we know what is the phase crossover frequency. Now at this phase crossover frequency, what is the magnitude of G of j omega? This is such that gain margin is 6 dB. So what is gain margin? Gain margin is 20 log mod of 1 by G of j omega. So from there 6 dB is equal to 20 log 1 by G of j omega. So this means G of j omega is equal to 0.5. Now what is the mod of j omega? This will be k mod by omega PCF multiplied by root under omega PCF whole square by a plus 2 square. So this is 4. And then omega PCF whole square, or you can say square plus 10 square, that is 100. And this will be equal to 0.5. We know the value of omega PCF, so we'll just include this value. So this will be k by root 20, root 24, root 120. So this is equal to 0.5. We solve this. What is the value of k that we get? This will be 120. So that means if the value of k is 120, then gain margin of the system will be 6 dB. Okay. Fine. So we'll proceed to next question. Or so what this says that for Nyquist plot a loop transfer function of form GS HS equal to this one, the number of counterclockwise encirclement of -1 J0. So again, this is the application of Nyquist stability criteria. By number of encirclement, we can say that this much, like whether the system is stable or not, but that is further thing, like later part. But first we have to show, like, see that what is the number of encirclement for this point. Okay. So we will just try to draw this Nyquist plot. So we can find g of g and of j omega h of j omega. That is the loop transfer function. This will be 60 by j omega plus 1, then j omega plus 2 plus j omega plus 5. Then this mod of g h will be 60 by root under omega square plus 1, omega square plus 4, and omega square plus 25. And angle of GH will be tan minus tan inverse because we have poles. So omega minus tan inverse omega by 2 minus tan inverse omega by 5. Okay. So with omega equal to 0, this g of h mod will be 60 by root 4 into root 25 into root 1. So 4 into 25, this will be 100, so 10, so this will be 6. And angle of GH will be tan inverse 0, which is 0. And omega tending to infinity, mod of GH will tends to 0. You can say G angle of G because this tends to infinity, so this will be 0. And angle of G of H will be, this is minus tan inverse infinity, so minus 3 pi by 2, because there are 3 minus 90-degree contribution by these three poles. So if we see the Nyquist plot in the GH plane, it will start from some point at angle 0 degree, and then it will go like this. This is at omega equal to 0, this is equal to infinity, and then we have a mirror image with omega equal to minus infinity, and minus 0 minus, this is 0 plus. So it is kind of this. Now in this case, this minus 1 J0 can be inside this region or it can be outside. So for that case, what we can do, we'll just find the value of this. We just have to say that at this point, the imaginary point component of g of h will be 0. So we just manipulate, or you can say simplify this one to find x plus jy type of term, and we'll set this y equal to 0. So from there we can find that whether this point is minus 1 or less than minus 1, greater than minus 1. This is the thing that we can do. This has been shown in the lecture. So this can be done. We'll just use this MATLAB command and just see whether where does this crosses and whether it encircles minus 1, and if yes, then how many times. Okay, so we have this system. This is ZPK 0, like no zeros, then one pole at minus 1, at minus 2, and one pole at minus 5, and we have gain which is 60. The system, we just see what is the Nyquist plot of this one. So NIQIST command will give us the Nyquist plot for this function. This is the plot. So this point, this red mark, is this minus 1, 0. And this is a plot that we saw that, okay, this will from omega 10 0, this will pass from 6 on the junction, then it will tends to 0 as omega tends to infinity. And if you can see, this Nyquist plot is not encircling this point minus 1, 0. So that means number of encirclement is 0. And one more thing that we saw, that it is like this. Okay. So this system is stable, and this answer is 0. Okay. Now let us proceed to next question. It says that okay, so this question is related to the steady state error. Before that, before this question, we went through this frequency domain analysis of system concept. So first we went through what is the steady state response of the system given the sinusoidal input to the system. Then we saw the stability margins, this phase margin, gain margin, how do you deal with this one, and then we solve for like what can be the value of gain for which this stability is guaranteed, and we went to Nyquist criteria also, that number of encirclements should be equal to the right half plane poles of a system minus this right half plane zeros of this closed loop system. So these things we saw, and now since in time domain analysis we after stability we had also seen the response of system to the input. So here also like what is the response of the system in the time domain is related to frequency domain response like of the system also. So in frequency domain, like for steady state error, we can also find here what is the error constant, and for that system in frequency domain analysis also. So this is a question related to that. Now it says that initial slope of Bode plot of type 2 system. Okay, so this is a type 2 system. So what would be the transfer function form? This will be numerator polynomial by denominator polynomial into s square. So two poles at origin, or you can say two integrators. Crosses 0 dB line at frequency omega equal to 2 radian per second. Okay. So find the velocity error constant of this system. So what would be the velocity error constant, or we can say, let us see what is the Bode plot. So at least we know that there are two poles at origin. So there will be in a plot, like a component, there will be some frequency plot due to ns. Suppose this is like this, and this is for ds. This is for s square minus 40 dB per decade. So the point at and the frequency response of Bode plot of this GS, this will be sum of these three plots. So if we see the initial part of the plot, this will be like this, minus 40 dB per decade, and the point at which this initial slope of this one crosses this 0 dB line is omega equal to 2 radian per second. Okay, so we have to find this velocity error constant. Now what is the value of velocity error constant? This is limit s tending to 0 s into gs. We try to find it, limit s tending to s ns by s square ds. So what would be the value of kV? This s tending to 0, this will have some value, some constant value, and this will tends to 0. So this will overall go to infinity. What is the value of this one? Kv equal to infinity. That means this error 1 by kV will tends to 0. That means for this system, type 2 system, this error, velocity error constant means, well, error to ramp input is 0, and this is obvious, we know from time domain analysis. For this system which is having this type 2 system, what will be the error constant that we can try to find out, because we know that this system will follow this unit step input, will track properly without any steady state error, and also ramp input. But if we provide parabolic input, so then there will be some error, because this is type 2 system, and then we can find the acceleration error constant. So for that, what do we know? That the magnitude of this one, so what is the magnitude? 20 log k, or we can say some value k by omega square, which is, because we are talking about initial slope, and this crosses this point at omega equal to 2 radians, so 2 square. At this frequency, what is the value of g of j omega? That is 0 dB. So this is 0. So this will be Ka by 4 is equal to 1, and K will be 4. So we can find acceleration error constant for this system. Okay. So what is the value of Kv that we have to find? This is infinity. Fine. Now let us proceed to next question. So what is the next question? This said that there is transfer function with Nyquist plot, this one. So this Nyquist plot, as omega tends to 0 to infinity, it passes from this point to this point. Okay. So let us try to find out what is the transfer function of system. So at omega equal to 0, what is the value of g of j omega? Obviously this is in gh plane, so h is 1, so this is g, and then g of j omega will be minus 1. So let us find which one satisfies this. So if we put s equal to j omega, and we will find the g of j omega. So if we see this one, this would give plus 1 by minus 1, because omega tends to 0. So this will be minus 1. So obviously this can be this is satisfying this one. If we find this one, so this is 1 by 1. So this will not satisfy because this is plus 1. If we see this one is also satisfying, but for this one, this is 1 by 1. So this is not satisfying. So at least we have two options, which is A and C. Now what we can do, we have to find which one of these is the transfer function. So let us see. Suppose omega is equal to 1. So we'll find what is the value of g. Suppose this is g1 and this is g2. So what is the value of g1? This is j plus 1 by j minus 1. Okay. So we just multiply j plus 1 whole square. This will be j square minus 1 square. This will be j square plus 1 plus 2j by minus 1 and minus 1. So this will be minus 2. This is minus 1 plus 1 minus 2j. What is this giving? This is giving j. So at omega equal to 1, what is the value of this one? G of j omega, it is j. If we try to find similarly for g2 at omega equal to 1, so g2 will be minus j. Or we have found something incorrect, or what? So this is j plus 1 and j minus 1. We just cross multiply this one. Okay, this is plus 2 of j omega, so this will be minus j, and we'll get this one as plus j. Fine. So what we say, that omega equal to 1, what is this crosses the imaginary axis, and if we say at omega equal to 1, this crosses imaginary axis, When does it cross imaginary axis? At this point, and at this point, what is the value? This is j omega, j1, you can say. So this is positive. That means this one is not satisfying this Nyquist plot. This G2 is satisfying, and G2 is the correct answer for this one. Okay, so let us move to next question. It says that a second order system GH, which is 1 by s squared plus 2 zeta s plus 1. So this is a standard second order system with omega 1 and natural frequency equal to 1 radian per second. And for different value of zeta, the Nyquist plot is given, and we have to find the relationship between this zeta 1, zeta 2, zeta 3, zeta 4. Now, if you see, this is a point of concern, -1, J0. So, more the Nyquist, if the Nyquist plot is closer to this one, that means this is tending towards instability. Now, if we see this, like try to correlate this with this time domain analysis, we said that, okay, suppose that this is the poles, this is again the another pole. So if we consider this complex conjugate pole, this is far from imaginary axis compared to this one. So that in that case, more farther from this imaginary axis, more stable the pole. So compared to this one, this is relatively stable, more stable. Relative stability is large for these poles. So as it moves towards imaginary axis, relative stability decreases. And in that case, if we consider Nyquist plot, so in that case, this lobes in the Nyquist plot will move towards this -1 J0 point. So this zeta 1, it is farther from -1 J0 compared to zeta 2, and like the Nyquist plot corresponding to zeta 1, that means the poles corresponding to zeta 1 is farther in the S plane. So this zeta 1 magnitude, or we can say zeta because this will be positive only. So zeta 1 should be greater than, because these poles are minus zeta omega in real part. So this will be farther, that means zeta 1 will be greater compared to zeta 2, compared to zeta 3, compared to zeta 4. So this is the relation between the zeta. If we see the Nyquist plot, so we can easily say that if this is a, with variation zeta, how the stability is, or we can say relative stability of the system is affected. So this is all. This session, I hope you have understood the concepts related to frequency domain analysis of system through this session. So we'll next meet in the next session dealing with the week 7 content. Thank you.